For centuries, astronomers have scanned the heavens with curiosity and wonder, charting constellations and mapping galaxies, believing the night sky to be a quiet, predictable place. But behind that calm facade lies something far more dangerous. Something that does not shimmer like a star or spiral like a galaxy. Something that does not emit light nor reflect it. These are the monsters of the cosmos, completely invisible, completely silent, and unimaginably powerful. You would never see them, even on the darkest and clearest of nights. They leave behind no visible trace, only strange signals from deep space. At first, they appeared as nothing more than distant points of radio emission, barely noticeable. But those tiny signals told a story that no one was prepared to hear. They revealed objects so bright they defied explanation, and so remote they seemed to exist at the edge of time itself. A single one of these beasts can unleash more energy in a single second than our sun emits in an entire year. And yet, they remain hidden, cloaked in darkness, feeding on stars, and sending deadly radiation across the universe. These are the Quasars, and their story is just beginning. In the early 20th century, the universe still seemed relatively tame. Astronomers had just begun to accept the idea of galaxies beyond the Milky Way, but the cosmos itself appeared quiet, structured, and knowable. That illusion shattered when radio astronomers began detecting faint, peculiar sources scattered across the sky. Sources that emitted powerful radio waves but were entirely invisible in optical telescopes. They did not look like stars. They did not resemble galaxies. They were simply points of mystery. One of those points, later known as 3C273, would change everything. In the early 1960s, astronomers tracked this strange radio source as it passed behind the moon, allowing them to precisely pinpoint its location. When they aimed an optical telescope toward that spot, they found a dim, star-like object. But its light held a secret. When Dutch-American astronomer Martin Schmidt analyzed its spectrum, he found familiar emission lines, fingerprints of hydrogen, calcium, and other elements. But they were shifted far toward the red end of the spectrum. This redshift was enormous. It implied that the object was receding at unimaginable speed, or that it was located billions of light-years away. Schmidt realized that 3C273 was not a nearby star, but something far more distant and powerful. It was the most luminous object ever discovered at that time, and yet it appeared smaller than our solar system. Something incredibly compact was releasing more energy than entire galaxies. It was a shock to the astronomical community, a puzzle with no known solution, and it marked the beginning of a new cosmic era, the era of quasars. The discovery of 3C27. 3 sent shockwaves through the scientific world. Something so compact, yet so bright, had never been seen before. But as more of these strange radio sources were found, astronomers were torn. Some argued that these were simply unusual stars within our own galaxy, perhaps exotic objects that redshifted their light in strange ways. Others insisted that the redshift indicated great distance, placing these objects billions of light years away and implying they were unimaginably luminous. The debate was fierce, and for years, no consensus could be reached. Because the optical counterparts resembled faint stars but behaved in radically different ways, astronomers gave them a tentative name: quasi-stellar radio sources. They were clearly not stars, but they appeared as point-like objects, just as stars do. Over time, the awkward term was shortened to a single, now iconic word: quasar. But the mystery of what quasars truly were remained. What kind of object could shine with the light of 1,000 galaxies, yet remain smaller than a solar system? Some proposed that these were young galaxies in their formative years. Others speculated they were powered by something entirely new. As radio and optical astronomy advanced, evidence began to pile up. The redshifts were real, the distances were real, and the brightness was staggering. But the power source still eluded explanation. No known physical process, no fusion reaction or stellar explosion could account for the energy output of a quasar. It would take another revolution in thinking to explain them. But for now, one thing was clear. The universe was far more violent, far more active, and far more mysterious than anyone had ever imagined. As astronomers studied more of these strange objects, a pattern began to emerge. Not all of them emitted strong radio waves, and not all looked exactly the same. Some blazed in X-rays, some pulsed with ultraviolet light. Others were silent in the radio spectrum, but still impossibly bright in visible light. A wide variety of galactic cores appeared to be releasing immense amounts of energy in many different forms. It became clear that quasars were not alone. There was an entire menagerie of energetic, compact galactic centers, each one extreme in its own way. To make sense of the growing confusion, astronomers introduced a new category: active galactic nuclei, often abbreviated as AGNS. These were the fiercely glowing hearts of certain galaxies, powered by an unknown but clearly immense energy source. Quasars became just one type of active galactic nucleus. Others included radio galaxies, whose jets stretched across hundreds of thousands of light years, and blazars, which appeared even more extreme, possibly because we were looking directly down the throat of their relativistic jets. It was as if the universe were showing us the same monster, but from different angles. Each new discovery added complexity to the picture. Some galactic cores seemed quiet in one wavelength, but erupted in another. Others changed their brightness over time, as if something were feeding or fading within. The diversity of these active galaxies puzzled astronomers, but one thread tied them together. At the heart of every active galactic nucleus was a core that burned brighter than the stars around it, often outshining the entire galaxy that hosted it. Whatever the engine was, it was not just powerful, it was universal. The zoo of galaxies was not random. It hinted at a common, underlying cause waiting to be uncovered. While astronomers were wrestling with the mysteries of distant quasars, a quiet revolution was taking place much closer to home. In the heart of our own galaxy, the Milky Way, something strange had long been suspected. Toward the constellation Sagittarius, radio telescopes detected a persistent, bright source of radio waves. It was invisible to the naked eye, yet unmistakably present in the radio sky. This source was catalogued as Sagittarius A, and within it lay an even more concentrated point of emission, Sagittarius, a star. No visible object accompanied it. No ordinary star or nebula could account for such intensity. As radio astronomy matured, so did our ability to peer into the dusty, crowded center of the Milky Way. Optical light could not penetrate the thick clouds of gas and dust that shrouded the galactic core, but radio waves could. And what they revealed was extraordinary. Tiny points of light, stars, could be seen orbiting around something completely dark. These stars moved at immense speeds, completing tight loops that obeyed the precise mathematics of orbital motion. And yet, there was no visible object at the center, only an invisible mass exerting a tremendous gravitational pull. By tracking the motion of these stars over decades, astronomers calculated the mass of the hidden object. It was more than 4 million times the mass of our Sun, yet all that weight was packed into a space smaller than the orbit of Mercury. There was only one known thing in the universe that could possess such density and remain dark: a supermassive black hole. It was a stunning conclusion. For years, black holes had remained theoretical, mathematical predictions of Einstein's general relativity. Now, here was one confirmed in our own galactic center, not through direct observation, but through the dance of stars around it. In the year 2022, that conclusion became visual. The Event Horizon Telescope, a planet-wide array of synchronized radio observatories, produced the first image of Sagittarius A star. What emerged was not a sharp picture, but a ghostly ring of light surrounding a shadow of pure darkness. The glowing ring was made of superheated plasma, swirling at nearly the speed of light, while the darkness at the center marked the event horizon, the point beyond which nothing, not even light, can escape. The gravitational pull was so extreme that light itself bent around the black hole, creating a warped, circular silhouette. Sagittarius. A star was quiet compared to the roaring brilliance of distant quasars. It was not currently feeding, and its surroundings lacked the chaotic energy of an active nucleus. But its existence raised an astonishing possibility. If our galaxy hosted a supermassive black hole at its core, perhaps all galaxies did. Perhaps the quasars that shined across the universe were not exotic outliers, but rather the same beasts, only in a state of violent hunger. The invisible monster in our backyard was not an exception. It was the key. The quiet shadow at the center of the Milky Way offered the first clear clue to the true engine behind quasars. At first glance, it seems impossible. Black holes, by their very definition, do not emit light. They absorb everything: matter, radiation, even time itself. So how could something so dark be responsible for the brightest beacons in the universe? The answer lies not within the black hole, but in the violent, chaotic region just outside its edge. Here, the laws of physics are stretched to their limits. Matter falling inward does not simply vanish. Before it crosses the point of no return, it unleashes an astonishing amount of energy, drawn not from nuclear reactions, but from the raw force of gravity. When gas and dust spiral toward a black hole, they do not fall straight in. They orbit, slowly losing momentum through friction and turbulence. As this material accumulates, it forms a flattened, swirling disk around the black hole, known as an accretion disk. Within this disk, particles collide and compress, heating the gas to temperatures of millions of degrees. The energy released is not stored deep inside like in a star, but radiated outward in real time, often in the form of high-energy X-rays and ultraviolet light. The disk becomes a furnace, and gravity is the fuel. To understand why this process is so efficient, consider the concept of gravitational binding energy. This is the energy required to lift an object out of a gravitational well. The deeper the well, the more energy is released when something falls into it. Near a supermassive black hole, the gravitational field is so steep that the act of falling itself becomes an engine. When gas spirals inward, a small fraction of its mass, often around 10%, is converted directly into energy. That is 10 times more efficient than the fusion reactions that power stars. But the system is not steady. It pulses, surges, and sometimes halts. As the gas heats up, it emits powerful radiation. That radiation exerts pressure, enough to push surrounding gas away and halt further infall. When the gas cools, it falls back again, repeating the cycle. This balance between gravity and radiation creates a kind of cosmic piston. Unlike a supernova that burns brightly and vanishes, an accretion disk around a feeding black hole can shine for millions of years, maintaining a luminous, near-constant output that outshines entire galaxies. This gravitational engine does not merely release light, it transforms the very structure of matter. As gas is pulled closer, its atoms are ripped apart into a hot, ionized plasma. Magnetic fields form within the turbulent flow, twisting and coiling like ropes under tension. These fields channel particles along curved paths, accelerating them to nearly the speed of light. Some of these particles escape, forming powerful jets that shoot out from the poles of the black hole. These jets can stretch for millions of light years, piercing through galaxies and bathing intergalactic space in radiation. What begins as a quiet swirl of dust becomes one of the most fearsome engines in the cosmos. It is not powered by fire or fusion, but by the relentless collapse of matter into gravity's deepest well. The accretion disk, with its fierce heat and wild radiation, is the visible sign of this invisible hunger. And when all conditions align, when gas, momentum, and gravity meet in just the right way, this engine awakens fully, illuminating the universe in a blaze of power. That is the heart of a quasar, a black hole made visible, not by its darkness, but by the fury of everything falling into it. The accretion disk around a supermassive black hole is not a calm structure. It is a maelstrom, violent, chaotic, and unforgiving. The gas and dust within it move at incredible speeds, swirling through magnetic turbulence and friction. Temperatures soar into the millions of degrees, transforming the matter into a plasma, a sea of free electrons and protons. In this environment, electric and magnetic forces take center stage. These magnetic fields do not remain passive. They grow, twist, and evolve, becoming the invisible scaffolding for one of the most dramatic displays in the universe. As gas spirals inward, it drags the magnetic field lines with it. The inner regions of the disk rotate faster than the outer regions, stretching and winding the magnetic lines into tight coils. This differential motion transforms the disk into a natural dynamo, amplifying the magnetic strength. The stronger the magnetic field becomes, the more it influences the motion of the plasma. What began as a gravitational engine now turns into a magnetic accelerator, capable of launching particles at velocities approaching the speed of light. From here, a new structure begins to emerge, twin jets of radiation. These jets do not originate from within the black hole. Rather, they arise from just outside its event horizon, in a region called the ergosphere. In this strange zone, space itself is dragged around by the black hole's spin, twisting anything caught within it. Magnetic fields that thread through the ergosphere become wound like springs under pressure. When they snap into alignment, they channel energy outward. Plasma caught in these magnetic funnels is hurled away from the black hole's poles, forming beams that stretch for millions of light years into intergalactic space. The process that powers these jets is still under investigation, but one leading explanation is known as the Blandford-Znajek mechanism. According to this model, the rotational energy of the black hole is extracted through its magnetic field, like a spinning turbine converting gravity into light. Charged particles accelerate along magnetic field lines, emitting radio waves, X-rays, and gamma rays as they go. These jets are so bright that they can be detected across the universe. Sometimes, the jets alone reveal the presence of a black hole long before the host galaxy can be seen. Inside the jets, matter races outward at nearly the speed of light. As these particles interact with surrounding gas, they generate powerful shock waves. Some of the particles strike photons in the surrounding area, boosting them into high-energy gamma rays. Others push against the intergalactic medium, inflating vast bubbles of plasma that can span hundreds of thousands of light years. These bubbles are not empty. They carry the heat and pressure of the black hole's fury, reshaping entire regions of space and influencing the evolution of galaxies on a cosmic scale. These relativistic jets are among the most extreme phenomena in the universe. They are focused, narrow, and persistent, sometimes active for millions of years. If one were aimed at our planet from nearby, it would bathe Earth in lethal radiation. Fortunately, the quasars that host such jets are distant, but their existence serves as a reminder of the power lurking in galactic cores. Where gravity, motion, and magnetic fields converge, the result is not silence. It is a brilliant scream across the fabric of space-time, echoing from the deepest wells of the cosmos. From Earth, the universe presents itself as a canvas of lights and shadows, but appearances can deceive. The violent core of a galaxy may look different depending on the angle from which it is observed. If we view the glowing accretion disk from the side, we may see the full profile of its radiation. If the radio jets are aimed sideways, we might detect a quasar, bright, distant, and steady. But if those jets point almost directly at us, the light becomes intensely focused, magnified by the effects of relativity. In such cases, we see what is known as a blazar, a quasar seen head-on, brighter and more violent than any other. This difference in orientation explains the diverse forms of active galactic nuclei. Sometimes the dust and gas obscure the disk, and we only detect faint emissions. Other times, the view is clear, and we witness the full fury of the engine. What we once thought were different objects, quasars, blazars, Seyfert galaxies, and radio galaxies, are now understood as variations of the same phenomenon seen from different perspectives. The monster is the same. It is the light, the dust, and the angle that tell different stories. And in this cosmic theater, where we stand makes all the difference. When we peer deep into the cosmos, we are not just looking across space, we are looking back in time. The farther our telescopes reach, the younger the universe becomes. And in that young cosmos, something extraordinary happened. Scattered across the ancient sky were quasars, fierce, brilliant, and far more common than they are today. These monstrous engines appeared only a few 100 million years after the Big Bang, when galaxies were still forming, when stars were first igniting, and when black holes were just beginning to feed. The early universe was not a peaceful nursery. It was a battlefield of creation and destruction. At that time, galaxies were closer together, tangled in gravitational dances that often led to collisions and mergers. These violent encounters funneled gas and dust into galactic cores, igniting black holes into full quasar activity. The feeding frenzy lit up the cosmos with radiation that traveled for billions of years to reach us. Some quasars in the early universe outshined their entire galactic hosts. Others pumped out more energy than thousands of galaxies combined. It was an era of cosmic adolescence, where chaos ruled, and black holes grew with staggering speed and appetite. But over time, the universe expanded. Galaxies drifted apart. The supply of cold gas diminished. The conditions that once fueled quasars became rare. Today, we see no quasars nearby. The beasts have gone quiet, their engines starved, their jets extinguished. What remains are dormant giants, sleeping at the centers of galaxies, including our own. But the echoes of their fury still ripple across space. The early universe belonged to them, and by studying their ancient light, we catch glimpses of a time when black holes ruled the night. The discovery of ancient quasars created more than wonder. It created a problem. These brilliant objects appeared when the universe was still in its infancy, less than 1 billion years after the Big Bang. At that time, the first stars had only just begun to shine, and galaxies were barely formed. And yet, we observe quasars that contain black holes weighing billions of times more than our Sun. How could anything grow that massive, that fast, in such a short cosmic window? According to our current understanding of physics and cosmic evolution, they should not be there, but they are. Black holes, as we know them, are born from the deaths of massive stars. These stellar corpses collapse under their own weight, leaving behind black holes that are a few times more massive than the Sun. From there, the only way to grow is to consume matter or merge with other black holes. But both processes take time, lots of time. Accretion is limited by radiation pressure. When a black hole feeds, the incoming matter heats up and glows, and that radiation pushes back against the infalling gas. This creates a natural throttle on growth, called the Eddington limit. The Eddington limit is not a hard wall, but it does make it difficult to grow quickly. For a black hole to increase its mass by a factor of 10 under this limit, it would need hundreds of millions of years. To reach billions of solar masses in less than a billion years requires a kind of feeding frenzy that defies the rules. Either these early black holes were born far bigger than expected, or they found a shortcut, one we do not yet fully understand. The universe seems to have grown its giants before it had time to build the ladder. Some astronomers suggest that the very first generation of stars, massive, short-lived, and composed only of hydrogen and helium, may have collapsed into unusually large black holes, hundreds of times the Sun's mass. Others propose that clouds of gas collapse directly into black holes, skipping the star phase entirely. There is even a possibility that some black holes were born during the first moments of the Big Bang itself, primordial relics from a time before light. Yet, none of these solutions are fully confirmed, and each raises new questions about the early universe. The existence of ancient quasars challenges the timeline of cosmic structure. It suggests that the universe was more efficient, more chaotic, and more extreme than our models predict. Perhaps gravity worked faster than expected. Perhaps matter clumped more easily. Or perhaps there are aspects of physics, still unknown, that shaped those early days. Whatever the answer, these ancient quasars are more than just brilliant lights. They are cosmic paradoxes, glowing signposts that tell us our understanding of time, formation, and growth in the universe may still be incomplete. If the first quasars are too massive to be explained by normal cosmic growth, perhaps the solution lies in something more exotic. One possibility is that black holes were born not from dying stars, but from the universe itself. In the earliest seconds after the Big Bang, the cosmos was a seething ocean of energy, density, and quantum chaos. In this strange state, tiny pockets of matter may have collapsed directly under their own gravity, forming what scientists call primordial black holes. These ancient objects would predate stars, galaxies, and even light itself. If primordial black holes exist, they could act as cosmic seeds, lurking in the young universe and growing rapidly as gas and matter rushed into them. Unlike stellar black holes, they would not be bound by the lifespans of stars. Their early formation would give them a head start, billions of years of uninterrupted feeding. Though no primordial black holes have been conclusively observed, their fingerprints may be hidden in gravitational waves, cosmic background radiation, or the structure of galaxies themselves. They remain a tantalizing and controversial clue. Another candidate for early black hole growth comes from dark matter, the invisible mass that dominates galaxies and binds the universe together. While dark matter does not interact with light, some models suggest it may occasionally interact with itself. In the dense, chaotic conditions of the early universe, these interactions might allow dark matter to clump and collapse, forming massive black holes. These dark matter-driven giants would not require stars or ordinary gas to ignite. They could grow in the shadows, hidden from view, until they lit up as quasars. There is also a third possibility, that the first stars were nothing like those we see today. In the early universe, gas was made almost entirely of hydrogen and helium. Without heavier elements to cool the gas efficiently, collapsing clouds may have formed truly colossal stars, hundreds, perhaps even thousands of times more massive than our Sun. These supermassive stars would burn hot and fast, living for only a few million years before collapsing directly into large black holes. If these stars were common, they could have seeded the first quasars with black holes already far ahead of the growth curve. Each of these possibilities, primordial collapse, dark matter structures, or giant first-generation stars, offers a path to explain the rapid emergence of quasars. None are proven, and each invites more questions than answers. But what they reveal is profound. The early universe may have been more violent, more creative, and more surprising than we ever imagined. To uncover the truth, we look to our most powerful instruments, like the James Webb Space Telescope, now peering into the ancient skies. Somewhere in that fading light may lie the origin of the monsters we now call quasars. For many years, astronomers treated black holes and galaxies as separate characters in the cosmic story. Black holes were seen as isolated curiosities, dense, invisible objects lurking in the shadows, while galaxies were vast islands of stars, gas, and dust. But as observations improved, a pattern began to emerge. It turned out that nearly every large galaxy harbors a supermassive black hole at its core. Even quiet, unassuming galaxies like our own Milky Way contain one. This was more than coincidence. It hinted at a deep, perhaps inseparable connection. The relationship goes beyond mere presence. There is a striking correlation between the mass of a galaxy's central black hole and the overall properties of the galaxy itself. The larger the black hole, the more massive the galaxy tends to be. The faster the stars move in the galaxy's central bulge, the heavier the black hole becomes. This link, known as the M-sigma relation, suggests that black holes and their host galaxies grow together. Somehow, the process that builds one also shapes the other. Black holes are not passengers in galaxies. They are co-architects. Quasars help explain how this connection works. When a galaxy experiences a burst of growth, perhaps triggered by a collision or a steady inflow of gas, its central black hole begins to feed. As the black hole consumes matter, it lights up as a quasar, flooding the galaxy with intense radiation and outflowing winds. This radiation heats the surrounding gas, making it harder for new stars to form. What should have been a galaxy-wide baby boom turns into a slow, regulated process. The quasar acts like a cosmic thermostat, preventing the galaxy from burning out too quickly. This feedback loop is crucial. Without it, galaxies might convert all their gas into stars in a cosmic blink, leaving them sterile and silent for the rest of their lives. But with quasar feedback, galaxies evolve steadily. Star formation proceeds over billions of years. Black holes flare, then fade, and the galaxy continues to grow, neither too fast nor too slow. In this sense, supermassive black holes serve as both destroyers and caretakers, shaping the long-term fate of the galaxies they inhabit. The discovery of this link has changed the way we see both galaxies and black holes. No longer are they separate entities, evolving in isolation. They are locked in a gravitational dialogue that spans cosmic time. The galaxy provides the food, the black hole regulates the growth, and in the quiet aftermath, a balance is struck, allowing structures like the Milky Way and perhaps even life itself to emerge. In this partnership, the darkness at the center becomes a guiding force, shaping not just the galaxy around it, but the destiny of the universe as a whole. Today, the center of the Milky Way appears calm. The stars orbit in silence, the gas clouds drift slowly, and Sagittarius A star, our central supermassive black hole, remains quiet, emitting only a faint trickle of radio waves. It does not blaze with radiation, nor tear stars apart in brilliant flashes of energy. But that silence may be deceptive. Just because a black hole is quiet now does not mean it has always been. And evidence is growing that the heart of our galaxy once burned with a much fiercer light. In the year 2010, astronomers using NASA's Fermi Gamma Ray Space Telescope discovered two massive lobes of high-energy radiation extending above and below the Milky Way's plane. Each lobe stretched for more than 50,000 light-years, larger than the entire galaxy itself. These structures, now known as the Fermi bubbles, were not remnants of supernovae, nor the output of ordinary stars. Their shape and energy suggested a different origin, an ancient eruption from the center of the galaxy, driven by Sagittarius A star in a far more active past. Computer simulations have shown that such bubbles could have formed from a single feeding event, a massive influx of gas, or even a disrupted star falling into the black hole. As the black hole consumed the matter, it would have lit up with the fury of a quasar, launching relativistic jets that pierced the galaxy's surroundings. Although short by cosmic standards, perhaps lasting only a few million years, that event would have transformed the Milky Way, flooding it with radiation and changing the course of its evolution. If that is true, then our own galaxy may have once looked like the quasars we now observe in the distant universe. A bright, blazing core surrounded by a spiral of stars. And if Sagittarius A star has been active before, it could be again. Black holes do not die. They only wait. One day, a new cloud of gas may wander too close. The quiet will end. And for a time, the Milky Way will once again become a beacon in the dark, a quasar reborn at the heart of our home. Far above the plane of the Milky Way, a silent journey is unfolding. The Andromeda galaxy, our nearest large galactic neighbor, is on a slow, inevitable collision course with us. Though it lies over 2 million light-years away, its gravitational pull is drawing it closer, and in roughly 5 billion years, the two galaxies will merge. This is not a catastrophic crash in the way we imagine car accidents. Instead, it is a graceful, slow-motion dance of stars and dark matter, unfolding over hundreds of millions of years. But for the supermassive black holes at each galactic core, the consequences will be profound. When galaxies collide, their central black holes spiral toward each other in a deadly embrace. They may orbit for hundreds of millions of years, losing energy through gravitational waves until they eventually merge into a single, even more massive black hole. But long before that final collision, chaos will erupt. Clouds of gas and dust, disturbed by the gravitational tides of the merger, will cascade toward the center of the new galaxy. That sudden flood of matter will awaken the dormant giants at both cores, igniting them into furious, quasar-like activity. The merged galaxy will not be a quiet place. Its core will blaze with radiation, jets may erupt from its center, and vast amounts of energy will pour into the interstellar medium. New stars will form in great waves, while others may be torn from their orbits and flung into deep space. For a time, the night sky will be transformed. From a safe distance, the light of this galactic merger would outshine nearly everything else in the local universe. And at the heart of it all, a reborn quasar may emerge, powered by the united fury of two supermassive black holes. For Earth, the future is more subtle. By the time this cosmic event unfolds, our sun will be nearing the end of its life. Life on Earth may be long gone, but the legacy of our galaxy will continue, etched into the fabric of a new structure, an elliptical galaxy forged from the collision of two spirals. Astronomers already call this future entity Milkomeda, and deep within its glowing center, the black hole that once slept in the heart of the Milky Way will shine again, marking a new chapter in the life of the cosmos. The ship is quiet, save for the hum of stabilizers adjusting against unseen forces. Outside the hull, nothing is visible, only the glow of distant stars and a pale haze of gas drifting through the void. You have spent years traveling toward this moment, across millions of light years, chasing a single point of light that outshines entire galaxies. And now, it fills your forward display, the core of an ancient galaxy, burning with energy beyond comprehension. At its heart spins a monster, a supermassive black hole, devouring everything around it, wrapped in an accretion disk so bright it eclipses the stars beyond. The ship begins its final descent. Radiation shields activate, plasma arcs in every direction, glowing in X-rays, gamma rays, ultraviolet flashes. Your sensors scream with data, temperatures in the millions of degrees, particles racing at near light speed. You are diving into the engine of a quasar, the most violent object in the known universe. The gas outside is no longer gas, but a storm of charged particles colliding and spiraling, guided by magnetic fields twisted into infinite loops. Time begins to distort. Space bends in directions that no compass can follow. As the ship draws closer to the accretion disk, the glare intensifies. You engage relativistic shielding protocols. The disk is impossibly thin, only a few light hours wide, but dense beyond reason. Beneath you, the plasma rushes around the black hole at a significant fraction of the speed of light. Friction and magnetic turbulence tear through it like lightning across a hurricane. Every photon of light is stretched and bent by gravity before it reaches your sensors, forming rings and shadows in impossible geometries. Behind the black hole, you can see the front of it. Then, the jet appears. A blinding shaft of energy erupts from the pole of the black hole, slicing through space like a cosmic sword. It is not made of flame, but of electrons and positrons accelerated to near light speeds, confined and directed by magnetic fields more powerful than anything ever created by human hands. This is a relativistic jet, born not from the black hole itself, but from the warping of space-time and the violence of magnetic rotation. Your ship is buffeted by shock waves as it passes near the base of the jet, riding the edge of a phenomenon older than Earth. You descend further, now well within the innermost regions of the disk. The gravity is immense. Every instrument registers distortions in space and time. Even light cannot escape in straight lines. Ahead, the event horizon looms, not a wall, not a surface, but a boundary of no return. It is surrounded by a glowing ring of bent light, a halo caused by photons that nearly escaped but were pulled back by gravity. The black hole does not shine, but the space around it burns. And within that shadow lies something we cannot see, cannot measure, and may never fully understand. You hold your position, hovering at the edge of eternity. Around you, the universe bends inward. Time slows. The past and future seem to blur. You think about the stars that gave their lives to feed this place, about the galaxies it has pierced with radiation, about the clusters it has heated with invisible fire. And in this moment of stillness, you understand. This is not merely destruction, it is transformation. The quasar is not just a monster, it is a furnace of cosmic evolution, a paradox of darkness and light. You turn the ship, set a course outward, and begin your ascent, carrying with you the knowledge that at the heart of every galaxy, including our own, waits something vast, ancient, and breathtakingly powerful. For all we have learned, the story of quasars remains unfinished. These cosmic beacons shine across the darkness of space and time, yet many of their secrets still elude us. The most puzzling among them is the question of scale. How do black holes grow so fast, so early? The earliest quasars we observe contain black holes with masses of several billion suns, existing when the universe was still a child. According to the physics we know, there has not been enough time to build something that massive through normal processes. And yet, there they are, burning brightly from the dawn of creation. Another enigma lies in the apparent absence of intermediate mass black holes. We have found stellar black holes with a few times the mass of the Sun, and supermassive black holes with millions or billions of solar masses. But in between, there is a strange silence. If supermassive black holes are built through mergers and steady feeding, then we should find evidence of this middle stage. Black holes weighing thousands or tens of thousands of solar masses. So far, such objects remain rare and difficult to confirm. Their absence challenges the narrative of smooth and gradual growth. There is also the mystery of the cosmic speed limit, known as the Eddington limit. When black holes feed, they shine. But that very light pushes back against the inflowing gas, placing a cap on how quickly matter can be consumed. The physics is clear, but the reality is messy. Some quasars appear to grow faster than this limit would allow, suggesting that nature may have found ways to cheat, perhaps through chaotic accretion, hidden geometries, or violent bursts that temporarily exceed the rule. If the laws are being bent, then we have more to learn about how energy and gravity truly interact. Even the role of quasars in galactic evolution is still being uncovered. We know that their radiation can regulate star formation, shaping the life cycles of galaxies. But we do not yet know how frequent those phases are, how long they last, or whether every galaxy experiences them the same way. Are all massive galaxies born through violence and fire? Or do some slip quietly into the night, never awakening their black holes into full quasar fury? The data is growing, but the patterns remain complex. The universe, it seems, resists being easily categorized. In many ways, quasars sit at the edge of knowledge, where observation meets mystery, and where theory collides with cosmic reality. They are both monuments to gravity and questions wrapped in fire. With every discovery, new questions emerge, and perhaps that is the most beautiful part of all. Quasars remind us that the universe is not yet finished revealing itself. There are still frontiers to cross, shadows to explore, and engines in the dark waiting to be understood. Quasars are not just distant curiosities or dazzling spectacles in the night sky. They are engines of transformation, cosmic regulators that shape the galaxies we see today. When a quasar awakens, it releases more than just light. Its radiation floods the galaxy, heating the gas between stars, stirring magnetic fields, and driving powerful winds outward. These winds can halt the formation of new stars by pushing gas away from the galactic core. In doing so, quasars prevent galaxies from consuming all their fuel too quickly, ensuring a slower, more stable evolution across billions of years. This regulation has profound consequences. Without quasars, galaxies might burn through their material in a brief flash of starburst, leaving nothing behind but aging embers. Instead, thanks to the influence of their central black holes, galaxies grow in balance, stars forming steadily, structures coalescing over time. Even the Milky Way may owe its temperate nature to an ancient quasar phase, long extinguished. That period of activity may have shaped the conditions that allowed our sun to form, and with it, the emergence of life on a small, blue planet circling quietly in a cosmic suburb. Across the universe, quasars act as catalysts of order within chaos. They are evidence that gravity, left unchecked, does not only collapse, it organizes, sculpts, and sustains. Every supermassive black hole at a galaxy's center holds the memory of this role, even when dormant. Though they no longer shine, they have already spoken their part into the story of the cosmos. And in that story, quasars are more than monsters. They are gardeners of galaxies, quiet architects of light, and perhaps distant ancestors of the very atoms that make us who we are. The story of quasars is one of extremes, of light born from darkness, of creation emerging from destruction. These radiant beacons, forged in the hearts of galaxies, embody the universe at its most powerful and its most mysterious. They begin with silence, with invisible giants asleep at the center of cosmic cities. But when awakened, they burn with a brilliance that challenges the imagination, flooding the cosmos with energy, reshaping galaxies, and echoing across billions of light years. Quasars are not merely objects. They are events, transformations, moments in time when gravity roars and the universe listens. And yet, for all their violence, quasars serve a quiet purpose. They regulate the growth of galaxies. They balance chaos with structure. They are evidence that even the most terrifying forces can play a constructive role in the grand design of the cosmos. Without them, galaxies might burn too fast or collapse too soon. Without them, the delicate pathways that lead to planets, to suns like ours, to life itself, might never have formed. In their fire and fury, quasars carry the seeds of stability. They are both storm and anchor, cosmic paradoxes shining with ancient purpose. As we look into the sky and see their light, we are not just witnessing distant phenomena. We are glimpsing the deep mechanisms that built our world. The same engines that once blazed in the early universe now sleep in our galactic core, waiting. Quasars remind us that the universe is vast, powerful, and still full of unanswered questions, but also that we are part of its story. Born from stars, shaped by gravity, and forever connected to the light that came before us. In the beauty and terror of the quasar, we see the cosmos revealed and ourselves reflected. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.